So this is a refresher of continuity and the IVT. Okay, so let's recall the definition of continuity. A function f is said to be continuous at the point x equals c if and only if the limit when x approaches to c of f of x exists, f of c is defined, and last but not least, the limit when x approaches to c of f of x is equal to f of c. In the first example, we need to use the definition of continuity to prove that the function is discontinuous at the given value of a. I don't need you to sketch the graph, okay? If you want to, you can, but it's not needed. Okay, so what are you going to do here? Okay, what you're going to do here is, number one, you want to find the limit when x approaches to 3. Okay, why 3? They are telling you to prove it at 3. Okay, so you are going to find the limit of your expression here. Okay, so what happens here? You know that we need to factor. Okay, so the limit when x approaches to 3, you factor. Okay, so we have something that looks like this. Okay, you cancel. Okay, and you have that this is equal to the limit when x approaches to 3 when x plus 2. So this is going to be equal to 5. So it exists. So condition number 1 met. Now what's the condition number 2? Condition number 2 is f of c is defined. Okay, so condition number 2, you know that f of 3 is going to be equal to the original. So you're going to have that it's going to be 3 squared minus 3 minus 6 divided by 3 minus 3. And what do you have here? 0 over 0, sad face, right? Why sad face? This is undefined. Or what you learned as undefined back in pre-calc. Okay, so this one exists now. So what can you conclude? Okay, because you need to justify your answer. Since f of c is undefined, okay, what do you know? We can conclude that, okay, the function, okay, f is discontinuous at a equals 3. Okay, do you need to write all the blah blah blah? Yes, you do. They are asking you to explain or justify your answer, so you need to be pretty clear why this is not continuous. Okay, let's look at the second example over here. Okay, use the definition of continuity to prove that the function is discontinuous at the given value of a. Okay, so what are you going to do? You have piecewise function. So in order for the limit to exist, you know that the limit from the left needs to be equal to the limit from the right when x approaches to 0. Okay, so you need to be careful with that. Okay, so let's compute those limits. Okay, for number 1, you know that the limit when x approaches to 0 from the left, okay, of this situation, okay, this is going to be equal to 2. Okay, now you know that the limit when x approaches to 0 from the right of x squared plus 1, this is going to be equal to 1. Okay, so what can you tell me here? Are they equal? Obviously they are not. Okay, so since 2 is different than 1, clearly, because you know your numbers, we know that, okay, the limit from x that approaches to 0 from the left of f of x is different than the limit when x approaches to 0 from the right of f of x. Okay, therefore what happens? Therefore the limit when x approaches to 0 over f of x does not exist. Okay, so f is discontinuous, okay, at the point a equals 0. Please note that I wrote a lot, Okay, why? I need to make sure that I'm justifying my answer. Okay, it doesn't matter. You need to justify your answer. Now, for this example, we need to use the definition of continuity to find the value of k that will make the function continuous everywhere. Okay, so the first thing that you want to see is you're like, what in the world? We have k's everywhere. What are you going to do? Well, don't panic. Okay, so first, let's compute the limit when x approaches to 2 from the left side, meaning you have 8x minus k. Okay, so this one, you know that it's going to be equal to 16 minus k. Okay, so this is your left side. Now, your right side is going to be when the limit x approaches to 2 from the right side, and you know that that one is going to be x squared plus k plus x. Okay, when you plug the 2 as normal, you would have something that looks like what? 4, okay, plus 2k. Okay, what do you want? You want them to be equal. Okay, so we want 16 minus k to be equal to 4 plus 2k. Solve that piece of cake. Okay, so you solve this piece of cake, and what happens? You have that k is equal to 4. Okay, so your new function, your redefined function, basically now you know that it exists. Okay, now you need to make sure that the f is defined, which you know that it's the same, and now you need to check if the third condition. Okay, so first condition, the limit when x approaches to 2 of f of x exists, so now that you know that it's true. Okay, now number 2, okay, you know that f of 2 is defined. Okay, you know that that's true because you have the equal here. Okay, now your redefined function is going to be f of x, and you have that it's going to be x squared plus 4x, 4x greater than 2, and then you have a x minus 4, 4x less or equal than 2, right? This is your redefined function. Okay, so you know that this exists because you plug the 2 here and you have something. Okay, now the question is number 3. What happens for number 3? Is this true? Let's ask ourselves, is this true? Okay, so you know that the limit is going to be what? When we plug the limit there, okay, the limit is going to be, you can plug it either here or here, and you know that the limit of this equation is going to be 12. Okay, so when you plug the f of 2, okay, f of 2 is going to be equal to 8 times 2 minus 4, which you know that this is going to be 16 minus 4, which is 12. So indeed, okay, so this is continuous. Okay, so basically with this beautiful k that we have over here, we fix the function. Okay.